זה יכול לקחת זמן.
Okay, let's start. So today we are going to continue discussing the problem of interacting fermions and how second quantization helps us do calculations in this kind of system. So this is the subject. Okay, and of course the most obvious physical system that we have in mind is the system of electrons in solids that are interacting. But the formalism is completely general, and later I will give some examples. So what is the problem that we want to solve? We have a Hamiltonian made of two terms. There's a single body part, H naught, and interaction part. And the single body part, usually it's some kind of Hamiltonian that contains a potential. It doesn't matter what it is. It's relatively easy to find its eigenstates and eigenenergies, and we can always express it in a basis that makes it diagonal. So H naught we're going to write as sum over lambda of epsilon lambda A dagger lambda A lambda, where lambda is some quantum number. And this contains momentum, spin, lattice height. We'll see a few examples later, but basically this is a general notation. And we know that we can easily find the ground state of this. Let me call it G naught. So the ground state of the system of fermions, here A and A dagger describe annihilation and creation operators for fermions. We know what is the ground state. The ground state is just a state where all the energy levels are filled up to the Fermi energy. Okay? So in fact, you can write it in this way. G naught equals a Fermi C. This is short for Fermi C. Or Fermi surface, but Fermi surface is very specific to cases where there is a momentum is a good quantum number, and you can write it as a product of, let me write it this way, lambda, which belongs to F, A dagger lambda acting on 0, on the vacuum. This 0 here is the empty vacuum. And you see that I only have one power of any creation operator for each lambda because these are fermions. Okay, and we know that A dagger lambda square is 0. So what is the definition here of the lambda? What do I mean by the notation lambda belongs to F? It means that epsilon lambda is smaller or equal to the Fermi to the Fermi energy. Okay, so if this is my spectrum, okay, I have a spectrum of many states. There is somewhere there's a Fermi level, and all the states below it are occupied, and all the states above are empty. Okay? Okay. So now I'm going to introduce an interaction here. The interaction will not be in the general case, except for some very special models that we will actually discuss in the next lectures. I hope maybe next week. But in a general case, we cannot treat it exactly. We cannot solve it. So we want to do some perturbation theory, or do some approximation, or use some trick how to simplify the problem and solve it. But let me first write down what it is. Quite generally, it can be expressed as a sum over 4 indices. And here I have some matrix element, lambda, lambda prime, mu, mu prime, and okay, maybe want it like this. And these are some matrix elements. And it describes all the possible processes where we annihilate two fermions with quantum numbers mu, mu prime, and recreate them as lambda, lambda prime. So, and we have to sum over all these processes. And one of the things that we would like to do as the simplest thing to make some progress is, if we are allowed to assume that the interaction is small in some sense and do perturbation theory, we can already gain some insight about the problem by, for example, just calculating the first order correction to the energies of the single particles, okay? And or to the energy of the system. So what is going to be the first ordering perturbation theory? This is always true in perturbation theory. You take the unperturbed Hamiltonian, which in our case is the single body part H naught, and you compute the matrix element or the expectation value of the interaction in the ground state, if this is a correction to the ground state energy, right? So we want to just compute the expectation value in the ground state of the non-interacting problem, okay? And now we would like to be able to compute such matrix elements in a simple way. And one of the problems that we face, that while the interaction terms contain only 4 operators, the state is a simple product of creation operators acting on the vacuum. But usually we think of a macroscopic number of particles. So there are a lot of operators here. And we want to simplify the calculation, because we know that if the interaction is just a small perturbation, what can it do to the ground state? When you apply it on a ground state, what does it do? It creates an excitation. But the excitations that are allowed are only excitations where you can take some fermion from the field Fermi C and promote it to an empty state. And you cannot promote a fermion to an occupied state, right? Because these are fermions. So there is a Pauli blockade, and because of that, it minimizes the allowed processes to only such type of excitations. Okay. Okay. So a nice way of looking at this problem, which I started considering 2 weeks ago, is to change our definition of the creation and annihilation operators in such a way that the ground state, this Fock state, the field Fermi C, will be considered as the new vacuum. Okay, so we want something that we want to have a formulation where this field state is the vacuum, and we create excitations above this vacuum. Okay, and we know, I told you from the beginning of the formulation of second quantization that choosing a vacuum and a set of creation and annihilation operator is a process where you have some freedom. Okay, so the definition of annihilation operators is with respect to a particular vacuum. If you change your definition of the vacuum, you have to change your operators. Okay, so this is what we're going to do first today. And so what do I really want to have? I want to replace the A's and the A daggers by operators that I will denote by C and C dagger, such that C lambda, for any lambda acting on the field Fermi C, will be 0. Okay? And if this is satisfied for any lambda, this is a legitimate definition of an annihilation operator with respect to this vacuum. Okay? Now, in our case, actually, the operator C will, in principle, be some combinations of the A's and the A daggers. I mean, they are, of course, related to them. And we can actually easily see what they are, but now the relation between C, the set of C's and the set of A's, depends on the quantum numbers lambda. Okay? Now, why is that? Let us first look at our original operators, and suppose I take my Fermi C and I apply on it some annihilation operator A with some lambda. Okay. Generally, I will not get 0, but in some cases I will. And let us see which are these cases. So let me rewrite it by, first I'm writing the state explicitly as a product of creation operators, and I'm denoting the index here by mu, just because it's a dummy index, to distinguish it from lambda, and all of these act on the vacuum. Okay. Now, what do we know about the annihilation operators A? That they will always give 0 if they are applied on the vacuum, on the original vacuum, 0, right? So this is something. This is how we we defined them originally, for any lambda. But now I want to ask you the following. In which case, or what is the condition that this will also give you 0? Lambda is not in F. Okay. Why is that? So that's actually correct. Why? Because if lambda is not in F, then write it. If lambda is not inside F, then what we can do is we can reshuffle it all the way to 0, right? And because lambda is not in F, it's not equal, lambda is not equal to any of the mu's here, okay? So we get something like this. We can write it, we can reshuffle it, and we get, and by reshuffling, I mean that you make transpositions with the next operator and then the next, and each time you do that, using the fermion anti-commutators, so this is equal to delta lambda lambda prime, and if lambda is different from lambda prime, the right-hand side is simply 0, and therefore when you exchange them, you just pick a minus sign. So I'm going to get, let me maybe write it, the factor first. I will get a -1 to the power p, where p is the number of transpositions or the parity of the permutation that you needed to do to reshuffle it all the way to 0. And then I get this, okay? So product of all the mu's, or all the mu's inside F, A lambda acting on 0, and this is 0, right? But if A lambda is inside F, then this is not what I get, okay? So depending on whether lambda is inside F or outside, in the first case, if it's outside, I get 0, so it acts like an annihilation operator. But if it belongs to F, I'm getting something a little different. First of all, again, I always get some phase factor minus or plus, depending on the parity of some permutation. But what I get here is a product over the mu that is, this is if lambda belongs to F. I reshuffle A and A lambda across all the A daggers which are different, just like what I did here. And then I never get any constant, just pick a minus sign depending on the parity of permutation. And then the mu equal lambda, I single out and I get something like this, okay? So I reshuffled it only through all the terms in the product that are different from lambda. But when I apply this operator on 0, what do I get? I no longer get 0. Why? Because when this acts on 0, it creates a particle, and then this particle is annihilated, and I just get 1 times the vacuum. Okay? So in other words, I'm going to get some phase factor times the product of all mu different from lambda. Okay, so all I did, what is actually this doing? It's not giving me 0. It creates an excitation, or it's a different state. Yes?
What's the minus the power p?
So again, in order to go from here to here or from here to here, it's of course not the same p, right? I'm writing it very schematically. You have to do a lot of, you have to do some permutation. And if the permutation is odd, you pick a minus sign. If the permutation is even, you get plus sign.
Even or odd number of shifts.
Right, yes, yes. So P is the parity of the permutation, okay? And I actually don't care what it is, because it is just a phase factor. So as we know, any wave function is defined, well defined up to a global phase factor, okay? So, okay, so what is this? What is this state? This is a new wave function. How is it different from the original ground state? So it's somewhere in all these occupied states. I actually created the hole. I created the hole at mu equals lambda. Okay. Okay. So that's what this is doing. Okay. So to summarize, A lambda is not an annihilation operator in general. It is only if lambda is outside of the Fermi system. Okay. Okay. So. I can already guess something about the C lambda, as you're going to see soon, can be identified with A lambda, provided that lambda is outside of the phase. Okay? What if lambda is inside the Fermi? See, I'm claiming that there is another possibility to get here an annihilation operator, and this is the following. I can erase all this, right? Okay, so let's take our Fermi C state, and now I'm applying on it a creation operator, a dagger, with lambda that belongs to F. Okay? Now, if lambda does not belong to F, what do I get when I apply it? I just add one more fermion. Okay, so that would give me another occupied state outside of the phase. Okay, but if lambda belongs to F, let's see what we get. Once again, we reshuffle it through all the, let me first write down the explicit form of the state. And now I do reshuffling of this through all the states, all the A daggers with mu different from lambda, until I hit A dagger lambda, right? Because now lambda is inside F, so one of the mu's here is equal to lambda. Okay? So I get a minus to the power of some permutation times a product of all the lambdas, all the mu's that are different from lambda. A dagger mu times. Now I'm left with a dagger lambda acting on, and it's squared because it's the one I single out the a dagger lambda out of this product, and I apply a lambda dagger once more. But what is this? And this, of course, acts on the vacuum. But what is this? This is zero because they are fermions. Okay? So this is the identically zero operator, and therefore I'm concluding that a lambda dagger acting on Fs is for lambda that belongs to F is also an annihilation operator. Okay? So my more general annihilation operator can be expressed in this way. I can split it to two cases. If lambda is inside F, it's actually given by the original creation operator of the particle, and otherwise it's the annihilation. Okay? So in fact, let me write this down in a little more nicer way. That later on we'll see will generalize to some more interesting cases or less trivial. So we define something that I will later call, okay, well, let me not give it a name, but it's a transformation from the A's and the A dagger to C and C dagger. And the operator, the mu annihilation operator, is defined in such a way. It is 1 minus, I will define it in a minute, theta F lambda A lambda plus theta F lambda A lambda dagger. Okay? Well, what is this F? So this is a theta function. So lambda F of lambda is defined as the theta, you know the theta function, right? It's the heavy side, gives you 1 only for positive arguments and 0 otherwise. So it's the theta of epsilon F minus epsilon lambda. Okay? This is its definition. Okay? In other words, it's actually the occupation. So if epsilon lambda is below the Fermi energy, it's 1. Okay? This is just reminding 1 if epsilon is smaller than EF. And let's make it, I mean, of course, when it's exactly equal to epsilon Fermi, you have to make a decision because it's a discontinuous function. But let's define it like this. Okay? All right? Okay, so this is just definition. So what I wrote here is how to interpret this expression. It looks like, in fact, a superposition of two contributions. It is a superposition, but it's a trivial superposition because the coefficients can only be 1 or 0, depending on whether lambda is inside or outside of the Fermi sea. So it's actually equivalent to this definition. Okay? But I deliberately write it like this because later on we'll see that for some different kind of ground states we can have new quasi-particle. We call this actually a quasi-particle. The creature that is annihilated or created by C and C dagger is a quasi-particle okay, annihilation. And later on we'll see cases where it is really a superposition, okay, of something that has some non-trivial weight on the annihilation and creation of the original particles. But this quasi-particle really behaves like a particle for any practical person, because what it actually describes, what this expression describes, that the quasi-particle is either a hole or a fermion. Okay? So it can be either this or this, or lambda outside of the, okay? Can either this or this, okay? And both of them are particles to any practical purposes, okay? Okay, and for these operators, the Fermi sphere is C. Sorry, is a vacuum, and we can easily derive, once we define an annihilation operator, we can easily define creation operator. What is it? It should be just the dagger of this one. And because the coefficients are real, it is simply given by a lambda dagger. If lambda is outside of the Fermi sphere, plus annihilation, which creates a hole, okay? And these hole or particle are more generally defined by this creation operator, okay? All right, so now what kind of particle is this quasi-particle? What is its nature? If the original particles were fermions, the new ones are also fermions. How do we know that? We simply have to check their anti-commutators. And we find that this is a really trivial transformation. So it's easy to show that if this is satisfied, and also we know that AA anti-commutator is always 0, and the same is true for the daggers, of course. So all this algebra is obeyed also by the C and C daggers. So C lambda prime dagger is a delta, and C lambda prime anti-commutator is 0. Okay, so the quasi-particles are fermions. And therefore, you know, there's no distinction between them and particles. I have to stress it once and again. You know, our definition of a particle is something that can be created out of a vacuum. And this is also the philosophy that guides the high energy physics of the particles that we recognize as real particles, like electrons, protons, neutrons, quarks. All of them are just defined with respect to some vacuum. Is this vacuum really empty? We never know. It's just a reference level. Okay? Okay. Great. So now let me give some examples of why is this going to be useful. So here I defined lambda as some quantum number, but we know that the physical example we have in mind is electrons in materials, and therefore we recognize that the quantum numbers will include usually a spin half for electrons, and another quantum number that can be either k vector if it's a free electron state, or a metal, which is, or a conductor, which is also described, as you know, by k as a good quantum number, or it can be a lattice index, or anything else. So okay, so let's first discuss as an example electrons in free electrons. So this is just a special case of what I've written here. Let me erase all this to make some space. So the first example is free electrons plus Coulomb interaction. Okay, in which case H naught is given by, so first of all, let me write down what are the operators. The quantum number lambda is going to be the wave vector k and sigma. So sigma can be up, down, or plus, minus. It's a two-state thing. And we can write H naught as sum over k, epsilon k, a dagger k sigma, a k sigma. Okay? Sorry, and of course the sum over k and sum over sigma. And unless there is some external magnetic field that provides the Zeeman effect, epsilon doesn't depend on sigma, but we can of course add very easily a sigma dependent thing. And if these are really free electrons, then epsilon of k is just a kinetic energy. Okay? Which is also true for semiconductors in the conduction band, but then M may be replaced by an effective mass, but doesn't matter. Okay? Now the interaction, so I'm not going to really treat it, just to demonstrate some way of looking at the problem, and later we'll do also a calculation. What is the interaction, the Coulomb interaction? Let me call it the interaction, not to change the notation. we can express it as a sum over Q of sum over Q of VQ rho of minus Q rho of Q. We saw it last lecture 2 weeks ago, where rho of Q is, so first of all, V of Q, let me just remind, is up to some normalization factor, it's the integral over it's just a Fourier transform of the interaction. And if it is Coulomb, then V of R is V square over the absolute value. Okay, this is just a Coulomb interaction. And most importantly, rho of Q, let me put here hats because these are the operators. Okay, V of Q is just a function, it's just a C number. Rho of Q is the Fourier component of the density operator. And if I want to express it explicitly in terms of these guys, then it's given by a sum over K and sigma of A dagger K minus Q and sigma and A K sigma. Okay, so what is this operator describing? Of course, if you Fourier transform it, you get back to the definition of the density operator, which is just local psi dagger psi at R. But in K space, it's very non-local. It's a sum over many contributions. Each contribution is describing a process where I annihilate an electron at state K and promote it to another state K minus Q. Okay? So when I take, and I can also write down the Hermitian conjugate of this operator. We discussed it last time. Because rho of R is a Hermitian operator, its Fourier transform is a Hermitian conjugate to its minus Q component. Okay, so rho dagger Q, actually it corresponds to just exchanging, so you can explicitly get it from this, but just reshuffling the dummy indices, you can easily convince yourself that it's given by the same expression, but with K plus Q here, which means that this is equal to rho itself of minus Q. Okay? All right, so let's take, maybe for convenience, I want to take, when I'm writing the interaction here, in terms of these operators, I now want to do perturbation theory, which means to take the expectation value of this operator inside the Fermi C, which in this case, what is the state that I named Fs? it is the product of all the k's where epsilon k is smaller than EF, namely all the k's that are inside what? Inside a Fermi ball, right? Because in K space, the energy, the kinetic energy of free particles is some quadratic expression which depends only on the absolute value of K, right? So the states that have energy below epsilon Fermi are enclosed by a ball of radius kf, right? And that ball is called a Fermi ball, and its surface is called a Fermi surface, okay? So I will draw it in a minute, but we also have to take, we account for each k, we also have two spin states for each electron, and the full Fermi sphere is just a product of all the k's inside the Fermi ball acting on the vacuum. So let me draw it. So I'm drawing K space. This is Kx, Kz, and Y. And the Fermi sphere, or the Fermi ball, rather, is here. Of course, what I'm plotting is in 3 dimensions, but also if it's 2-dimensional, it's much easier. It's going to be a circle, and what happens in 1 dimension? If I have only 1 dimension, how does it look? It's actually just a line between 2 points, okay? So this is how it looks. There is some, the radius is K Fermi, where K Fermi is defined as the K vector that corresponds to the Fermi energy, very simple. And all the states, this is this is how the ground state looks like. All the states inside the ball are occupied, and everything else is empty. Okay. Now, when I'm applying a density operator on this, and let me take rho Q, because it's simpler to. Okay, so what will I get? First of all, I will get many contributions. I will get a sum of things, okay? But some of the terms here will give me 0, right? Why? Because if, so let's take this expression, right? So if K is outside of if K is outside of the Fermi sphere, and K plus Q, or at least if this is outside of the Fermi sphere, or if this is inside, I get 0, right? Okay, in both cases, because first of all, I cannot, if I apply an annihilation operator on any K state outside, I get 0. If I apply a creation operator on a state that is already occupied, I also get 0, right? So, in fact, I'm going to get non-zero, so I'm not writing the full thing, but the only case where I get something non-zero is from the terms that look like this, where K is inside, or if you write it in terms of energies. If K absolute value is smaller than Kf and K plus Q is bigger than Kf, then if I apply this on the Fermi surface, I can actually rewrite it as a product of two creation operators. Where the new creation operators are now what I defined as C and C diagonal. Okay, C diagonal. So what is this doing? This C dagger, which is in fact an annihilation of an occupied state, is creating a hole, right? Use colors. So I'm creating a hole at some K inside the ball, and let me define this vector as Q. Okay, so the vector K plus Q is outside, and I'm creating a particle outside of the first. Okay, so this is what any kind of such operator does. It creates an electron-hole pair, which simply means that you promote one of the occupied state outside. Okay? And this is called an exciton. Okay? It's this whole thing is not a fermionic excitation. In fact, it's bosonic in nature. If you think of its statistics, you can relate it to some bosonic object that is made of a pair of two fermions, an electron and a hole. But and we discuss it in more detail next week probably. But either way, it is creating something. It's an excitation of the Fermi surface. It is not vanishing. And when you sandwich it with its dagger, you're going to get some finite contribution. Okay? And then to calculate the expectation value of the interaction operator, you just have to sum over all these contributions. Okay? That's what you do. And you see, I don't need to work here with a lot of operators because I only have, eventually we're going to see that we can express everything with expectation values of very few numbers of operators. Okay? This is for any two-body interaction we can do. Okay, so this was an example where the basis that I chose for the single body part was momentum because it's a good quantum number of free particles. But in many more interesting systems, which are materials that are not metals, okay, metals are very trivial states of matter. Okay, I mean they're beautiful. They have many good properties, many positive properties, but in terms of states of matter, they're kind of simple, although there's something that I will show you later on. We know that metals are very well described by free electrons. It's a good approximation. But the interaction, there is a Coulomb interaction, right? Because electrons are repelling each other by Coulomb interaction. And the Coulomb interaction is not small. It's actually not trivial to justify why we can neglect it. We'll discuss it later, okay? But there are even more interesting states of matter. And usually you find them in materials that are not good conductors, and where the quantum numbers that describe the electrons are not necessarily or the useful quantum numbers, right? Because you can always use any quantum numbers you like, but the good starting point may not be momentum, but rather some local coordinates, okay? And this is when you have a lattice. So I'm going to describe a class of such interactions that are much better described in a different basis. Okay, so let me erase this. Okay, so this will be our next examples. So this is in a generic solid state problem. We want to think of a crystal that is, let's forget now about impurities, disorder, all this stuff is complicated. I don't want to consider it for the moment. Let's assume that it's small. So we have a crystal. Crystal is a periodic structure, and it defines a very natural quantum number, which is the location of the Bravais lattice, for example. Okay, so we're going to assume that the useful quantum numbers for us, apart from, of course, the spin, which is very important, is not K, but it's what I will denote by I, an index that corresponds to Ri is a lattice site. Okay, so you have some let's say let's take a triangular lattice, for example, or a square. Doesn't matter, but the i's they are indices. They're indices that, you know, depending on dimensionality, you can order them in some way that denote the location of an atom in the lattice, okay, in the periodic lattice, okay. And usually we want to think of a Bravais lattice because that's the basic structure, and maybe inside the unit cell we have some other degrees of freedom, some internal degrees of freedom, but that's, let's just think of the simplest thing. Okay, and the quantum number will be this I and sigma, okay, that is still there. Okay, so now in which case it is useful to work in such a basis, because we know that if it's a perfect crystal, and if we have no interactions, then actually you can write the Hamiltonian in a lattice basis, but then if you diagonalize it, you once again find that the eigenstates have a quasi-momentum. The correct or the eigenstates of the perfect crystal are Bloch functions. I hope you remember all that, right? They're Bloch functions. The quantum number is very much like K. It's actually a quasi-momentum. It's defined within a Brillouin zone and so on, but it is still like momentum, right? So why do I insist on going back to this? Because in many cases where the material is not a good conductor, and usually when you think of complex oxide compounds and materials that are more interesting, that have magnetism, that have superconductivity, they have, I don't know, charge density wave, all sorts of more exotic states of matter. The single particle, the single body part, is not the dominant term in the Hamiltonian. The interaction is more important, and the interaction, which originates from Coulomb, right, it decays with the distance, and therefore it's actually favoring local states. Okay? So an easy or a convenient way of writing the interaction is in terms of I and not K. Okay? So that's why. So we're basically thinking of a problem where the electrons are. You have electrons that are closely localized on some sites, okay, and they are described by these one-year functions. Let me just remind you. So if this is the look at some axis in space where this is the lattice site. And the wave functions that we're thinking of, typically they look like this. This is called the phi, let me just call it phi I. Okay? This is how they look like, typically, something like that. And we're going to define operators A dagger I sigma that acting on the vacuum will give us a wave function. So like this, if we look at their overlap with real space, they will be just these linear functions. Okay, this is what they are. Okay, so in other words, simply said, A dagger I sigma creates an electron on site I with spin sigma. Okay, and now we can write the single body Hamiltonian in this basis. And what is its generic form? You remember how it looks? This is the so-called tight binding model. So H naught is actually, usually it's a sum over bands, but let's assume that we have just one band, just for simplification. So we have one local term that is in fact completely trivial. Why is it completely trivial? Because of the periodicity of the lattice, this site energy is just a constant. Okay, and therefore So let me finish writing the whole thing and then we'll discuss. And then I have a sum over I and j of something that I call Tij AI bigger aj plus Hermitian conjugate. Okay? Epsilon, you are familiar with this, right? Or maybe not in the second quantization language, but this is the tight binding expression where epsilon describes an on-site energy. It's related to the atomic level or to the top atomic level or something like that. And Tij is called, let me just remind, this is a site energy. And T is hopping. Coefficient. Why is it called hopping? Because it describes the amplitude for a process where you hop an electron from site J to site I. Okay, or vice versa, and of course, if T is real, then the Hermitian conjugate is just AI AJ, right? But T doesn't have to be real. Okay, it describes a hopping process. So if this is, let me, I and this is J, there are two different sites. They don't have to be nearest neighbors. In principle, Tij counts over all the pairs of sites. And if you want to write an exact expression, right? And the term, this term describes a process where, okay, let me erase this. This is the process described by such terms, okay? And Tij is a number that describes how probable it is, okay? Now, it is actually getting smaller and smaller with the distance, because if the state of the system is that the electrons are closely tied to their sites, then this is coming from some probability of overlap between them. Okay, so it's getting smaller and smaller, and usually in the tight binding approximation, we neglect all the contribution except for the nearest neighbor. Okay, so yeah, so I'm just reminding the tight binding limit is where sorry, I still owe you to mention why is the first term trivial. Yeah?
This process is Markovian for now? Or in
What do you
general?
mean by Markovian?
I mean,
it's an opera, the AI.
No, but the constant T. The constant T.
There's no, yeah, everything here is, there's no timing. I mean, if we want to discuss time dependence, we have to introduce, phase factors to describe time evolution. I'm not describing time evolution. I'm discussing static program. Okay? Of course, you can use this language to compute time evolution. Okay? So, but when I say process, I mean, you think of a scattering, something that happens with time, but it's just, it is just an operator that promotes a particle from one side to another. Okay? And its conjugate is the opposite. Okay, so in the first term is usually some constant that you don't care about. Why? Because what is this operator? This is a local operator, A dagger I sigma, AI sigma. What is it? It's just the number operator. This is the number operator for particles on site I and sigma. And if you sum over all the i's and all the sigmas, what do you get? Just the total number, right? So this whole thing this is nothing but the total number operator. Okay? So a constant epsilon is just something that adjusts the definition of the chemical potential, because we know that if we do statistical mechanics for that, for example, and introduce a chemical potential in the grand canonical ensemble, it's just minus mu times n, right? So here the epsilon sets the zero of level, if you like. Okay, so it's not it's some global constant, but the second term is the one that has most of the physics, and therefore in the tight banding, I mean, sometimes you can include the epsilon, it doesn't matter. So let me just write it here, but typically you write it, sorry. In the tight binding approximation, you neglect all the terms in this sum except for the nearest neighbor. And this hopping coefficient you denote by t. So you write it like this. Integral aj plus, okay, this is how it looks like. Okay, and t here is a constant, is a parameter. Okay, and if you want to include next nearest neighbor or more hopping processes, you call them t, t prime, t naught, t1, t2. Okay, but this is the simplest version. Actually, we know that if we just diagonalize this, what do we get? We get energy bands that look like a cosine of k something, right? But we don't want to diagonalize it. We want to keep it like that. And in fact, so the problems that now I'm going to be interested in, this term may be small, okay? And that is the one that will treat perturbatively. Okay, so it's the opposite limit. So we want the interaction terms to play the main role. Okay. Great, so now having that in mind, I'm going to classify the type of interactions you can have. So first of all, before I do that, I want to write the interaction term in general, and write it. So what am I doing? I'm going to, once again, I write the interaction. I chose a basis for H naught. And now I'm summing over all the possible indices and all the possible scattering processes. But notice that I have in mind something like the Coulomb interaction, which originally comes from density. Okay? So it doesn't involve by itself processes that scatter with a spin. So when I write it down, I write 4 indices for the lattice sites, but only 2 for the spin. Okay? So let me write it explicitly. So it's I, J, sorry, let's use the same convention that I had before. I prime, J prime, and then I have a sigma and a sigma prime. Here I have a matrix element that in the general case I write like this, and you see it's not dependent on spin. I'll define it soon. And now I have a dagger I a dagger I prime sigma prime, a J prime sigma prime, a what did I do? Yeah, sorry, and this is J sigma. Okay. Okay, this is what I'm writing, and you see that. So I'm allowed to the interaction, which boils down originally. It's coming from something that is defined as density in real space, right? V of R times rho R square, if you like. Then there is a trivial summation over the spin indices, but it can involve transitions between lattice sites. And let me now write what is the matrix element I prime, J prime. It is the integral in d-dimensional space of phi star, actually I need a double integral. R prime, okay. And now what do I have inside the integral? I have phi I star of R, phi I prime of R prime star, and here I have V of R minus R prime, so I'm assuming interaction that this is the electron-electron interaction that depends only on the distance, and we have in mind the Coulomb interaction, but it doesn't matter. And now I have phi J prime of R prime and phi J of R. Okay? That's what it is. Okay, so in fact, to get this form, I started from interaction on the form of integral over R prime of rho of R, rho R prime, V of R prime, and this is what I did. Okay. Now, what are these phis? The phis are what I defined as, these are the Vanier functions, just reminding you how they look like.
Still on the bottom.
They are very, very localized. Okay, these are, so phi, okay, where R is the distance from Ri, okay. So, and typically they're localized over the size of an atom, which is angstroms, okay? So they're very localized, and notice that forget about what the interaction is. Coulomb interaction decays with the distance, but it decays slowly, right? Just 1 over R. So it's long range. But the matrix elements may decay much faster than the interaction itself. Why? Because here I have different lattice sites, and the overlap between them is very small. It's in this state where you actually have some destructive interference. So actually, there may be an exponential decrease in the matrix elements if you consider indices with very far apart sites. Okay? So that's not because the Coulomb interaction is local. It's because the wave functions in this basis are localized. Okay? Yes?
Just a moment. But you define T, it's not a neighborhood. I mean, the T, so
T is not an interaction. T is a single body. Yeah. T is a single body, and I don't want to spend time to just remind yourself what it is. It is actually, if you take the Hamiltonian, when you write it as a Schrödinger equation in real space, right, minus h bar square nabla square over 2m plus v of r, where v of r is the periodic potential. If you plug it into, look at the matrix element between I and j, you get something. This something you call T. Okay? So it's a single particle parameter.
Yeah. I mean, it's not my question. I thought that just the T, I mean, it's between neighbors, but now I see it's between everybody.
Yeah, so actually, so now I'm actually back to, so you're right, this is an approximation, okay? This is an approximation that just reduces the number of parameters we have to deal with. But when you think about the interaction, you are right. Actually, now there is also some decrease with distance. Absolutely, for the same reason.
Yeah, this is what I wanted
That's
to
right.
ask. Yeah.
Okay, good. But there is, and indeed, therefore, just because of that, I'm not going in general to be interested in all the possibilities, but once again, I'm going to identify the leading ones, okay? And however, unlike here, where the leading one is just one parameter, there are more possibilities, okay? And therefore, I'm going to classify them, and indeed, in most cases, people don't look at models that include more than one or two of the ones. But I'm going to classify them according, because here you see you have more possibilities. Of course, in general, you want all these wave functions, all these i's and j's to be close to each other. But you don't necessarily need all of them to be the same. Okay, that will be one term, is the purely local, is going to be the one we're going to consider it. But before that, let me just do a classification here, okay? So, okay, I guess this we can erase. And now I'm going to do So I'm going to look at some special cases of the choice for these indices. And the first one is going to be something that I will call direct terms, or Hartree. Hartree is named after a person, but y direct, you'll see in a minute. And what are these? They correspond to the case where I equal j and I prime equals j prime. So therefore we reduce the four parameters in the sum to 2. Okay, and we define a matrix element uij which uij where, because it depends only on 2 indices, let me give it now a new name and I just call it Vij. Okay? Now, okay, so what is it? So let's look at the interaction term that has this coefficient. So it's a term in the interaction, it's a subterm where, let me see what, so let me call it, okay, I will not give it a name, let me just write the expression, what kind of process it describes. So it's ij.
Isn't it supposed to be like iijg?
No, because of the way I defined, notice that there is some way where there's some order where, okay? This is the convention we use throughout the whole course.
Right.
Okay, so what is the process that it describes? It's the following. You know what, let me just give it a, sorry for being a little hesitant on this. Let's call it V Hartley. Okay, so I'm just accounting for all the contributions over ij and sigma prime Vij. And then let me write down what we have here. AI sigma, AJ sigma prime, AJ sigma prime, AI sigma. Okay? This is what it is. But you see that I can express it in a more compact way, because if I just take this product, what is it? It's the number operator at site j and spin sigma prime, and if I sum over all the j's and all the sigma primes, I get just the number, or actually, no, I don't want to sum over j because Vij depends on j. So if I sum over all the sigmas, I just get the number operator for electrons on site j. Okay? And similarly, okay, so I can notice that it is maybe not written very clearly, but I can take this and sum it over all sigma prime, and then I get just nj, the number operator nj, and I can at the same time take the product of these, which is nothing but the local ai dagger sigma ai sigma. I sum it over all sigmas, and this gives me another number operator, and altogether this Hartley term can be written, and this is why it's called direct also. It boils down to a summation over ij of Vij of n I and j. Okay, so it's again something that looks like a simple density-density interaction. I have some number. If I calculate its expectation value, it's going to be something that in fact has a simple classical analog, because it's just the number of electrons in state on site I times number, or the occupation of site I times occupation of site j times the coefficient. Okay, that's all. So here let me just write the definition. Ni is the sum over sigma of A dagger I sigma A I sigma. So you sum over the spin indices, but you're left with some local number operator. Okay? And therefore, how many electrons can exist on each site? Just 2. Okay, that's the maximal expectation value of n. Okay, now if we also look at the matrix element, this Vij, what is it? It's actually a special case of what I denoted here as a U, and it is given by, so it's the case where this I is equal this, and this is equal to that, right? If we write it explicitly, integral dr prime, and now I have phi star of j r prime, v of r minus r prime, phi of the same j at r prime and the same I at r. Okay? That's what it is. And let's see what this is. So V is some interaction, and decay is a distance, but what I'm looking at, if and notice that these are just numbers, they are not operators, so I can reshuffle them. Phi star times phi of the same j and the same r prime, what is it? Just the absolute value square of the function phi j, right? So this is phi j of r prime, absolute value squared, right? And similarly, this factor is phi I star times phi, the same I, the same R. So this is nothing but the absolute value square of phi, right? So this is very important to notice that this is always positive, right? So the sign of this matrix element is guaranteed to be equal to the sign of V. If V is a repulsive interaction, it will be positive, okay? And what are these describing, in fact? These are nothing but some description of the probability to find the particle site I or its, okay? Yeah.
What is the limit of the integral of R? It's between the sides or
So the integral, the integral is over a continuous space, okay?
but it's from one side to
So
other?
you have a continuous space, but you are converting it to, I mean, the good quantum numbers of your Hilbert space are defined by lattices, okay? Because these are electrons on a lattice. So it's nothing but this expression in general is converting the interaction in the form in double integral over r prime of rho of r, rho of r prime, v of r minus r prime to lattice, okay? Okay. So you write that, you know, I and J are also local, but they are local much more specific. Okay, they are discrete sites in a periodic crystal. Okay? Okay, and now,
Can you
yeah?
just repeat what you said again? But, okay. This is positive and this is positive.
Right, so if you look at what will contribute, in order to get a finite or non-negligible Vij, I noticed that, and the interaction, let's assume that it has one well-defined sign, like it's,
Okay.
for example, positive,
Okay.
repulsion, okay?
Okay.
Then it's very easy to see that Vij will be, first of all, it will have a well-defined sign that is dictated by the interaction, whether repulsive or attractive. So let's say repulsive, and then the weight, it's multiplied by some weight, and this weight is a positive number, right?
Yeah.
And clearly it decays with the distance between I and J, right? So for practical purposes, the overlap of this, because I is different from J here, and actually I should actually be a little more careful and define it like this, because the case I equals J is something else, is special, okay? It's fully local. But for I different from J, you get something, but depending on the distance, it will typically decay exponentially. And that's because of the overlap of these two very well localized wave functions, okay? So, yeah, so usually for practical purposes, we'll just take the nearest neighbor, okay? Okay? Okay, so this is what it is, and the reason that it's called direct is really, this is something that has classical analog. You just have to look what is the occupation of two sites, and the interaction describes the interaction between these two electrons. Okay, okay, so that's the hard trick there. And I went over time, so let's take a break. Okay, half an hour break, and we'll go to the more interesting. Okay, I suggest that we continue. So, yeah, so now we're looking at the second special case. Actually, let me leave just the definition of so the second type of interaction terms is called exchange, okay, or after Fock, the same guy from the Fock-Hilbert space. So this is the case where once again there are two pairs of indices that are the same, so we are reducing it to only two, I and J, but unlike the direct term, it is Ij, and the second two we exchange. Small difference, okay? But then now let us see what it describes. And this is what, because once again it depends only on two indices, let's give it a name, J, IJ. We denote it by the letter capital J. Okay, so what does it describe? What does it mean to exchange the two last indices? The terms that are contributing to it are of the form AI dagger sigma, A dagger J sigma prime, just like before. But now we are maintaining the same spin label, but exchange the order of I and J, and this we write as I sigma prime, A J sigma. Okay? Okay? Clear? And of course, this multiplied by Jij, we sum over all possible spins, sigma and sigma prime. And now let us look at what this kind of operator does, and we realize that this is not actually a term that doesn't really have a simple classical analog. Why is that? Because you see, there's nothing here that I can represent as a local, in the basis of the lattice sites, I cannot represent it as a local density or a local number operator, right? So what does it describe? I have my two sites, I and J, and the process I'm describing here is the following. I take this term, it's a product of two hopping processes, if you like, or hopping operators. One of them takes an electron with spin sigma prime from I to J. So this is for spin sigma prime. And at the same time, it takes an electron with spin sigma from J to I. So this is a simple diagram that describes this process. And now you can easily see why it's called exchange, right? So what are we doing? We are taking two electrons. By the way, sigma and sigma prime can be, either of them can be any spin, so they can be the same spin or different spins, and we'll distinguish the two cases. But whatever they are, what are we doing? We're taking two identical electrons and exchanging them. Okay? And keep in mind that these are fermions. So this is allowed to be taken into account even if they have the same spin, right? So we can just exchange between them. And what we expect when we exchange two fermions, we expect to have, because of the Fermi statistics, we expect to get a minus sign, okay? So, as a matter of fact, if you look at a subset of such processes where sigma is equal to sigma prime, you see that it is actually a term that also exists in the Hartree part, in the direct part. In the direct part, let me maybe just for clarity, I will write it again. It has this thing where here the I of sigma goes to I sigma J2, okay? And once again, inside the direct term, I'm summing over all ij's and all sigma and sigma prime, and in particular, there is a term, or there are in fact two terms with sigma equal to sigma prime, right? For each I and j. Here, there are also two terms with sigma equals to sigma prime, and they do exist also here, right? What is the difference? So let's take the case sigma equals to sigma prime, and see what we get. So all the sigmas are, it's only one sigma, okay? And we see that if we exchange these two, we are back to we're back to the Hartree. So the Hartree and the Fock terms have have a particular contribution where assuming that the coefficients of both of them are positive, and if we have a repulsive interaction, let's say, the wave functions, so for the exchange term, maybe it's not so obvious, but if the sites are very close to each other, the overlap between the wave functions will still recover the sign of the original interaction. Okay? Which means that if the coefficient of the coefficient j is positive, we can interpret this term as a negative contribution to the direct part. Okay? So, in other words, what does it say? It says that the exchange term favors spins of nearby electrons to be the same. Okay? The system actually can gain energy, in a sense, by placing, if you have to put two electrons close to each other, it's better to have them with the same spin. Why? Because then, once again, this is going to give you a contribution that if you just exchange the operator, will give you a negative contribution to the energy. It will cancel or partially cancel the Hartree term. Okay? Now, the physics of it is very simple. The Pauli blockade naturally tries to distance electrons from each other, right? Because you want them, you don't want to put them on the same site. So if you have a repulsive interaction, the Pauli principle reduces it. It reduces its effect, in a sense. So it's not that it's turning the interaction from repulsive to attractive, but it reduces the repulsion. Okay? Okay, and the consequence of that is, and I hope you're going to get a homework exercise that will explicitly demonstrate it. The consequence of that is that because of the repulsive Coulomb interaction, the electrons on the lattice will try to order themselves with equal spins. Okay, they will tend to order themselves with equal spins. In other words, yeah. So that's actually it's a Hund's rule, or in other words, it gives you a tendency for ferromagnetism. Okay, if and now it's not always, of course, you always have such interaction. You don't always have ferromagnetism. Why? Because in most cases, the kinetic energy of electrons will dominate so much that it will not allow, it will compete with this. Okay? The kinetic energy would rather have the electrons not ordered on sites, right? So, but if the kinetic energy is for some reason suppressed, so if you have, for example, a crystal material with very narrow bands, that's a typical example, and you can have such situations in nature where the interaction is the dominant term. You can have ferromagnetism. Okay? Now, it's not necessarily the only mechanism for ferromagnetism, and it's not what makes iron ferromagnetic, for example. It's not a good example, but it is a mechanism for ferromagnetism. So, and in fact, you can show that there is a mapping. If you take the exchange interaction, writing it as sum over I different from j, jij, and here I'm writing sigma prime, j sigma prime, a, I, j sigma. So this, with some algebra manipulation, can be mapped into the following expression, I different from j, of jij. Okay, this plus, there is some correction, from the density. So there is an identity that can take you from here to here. Now, what is the first term here? This is what you are familiar if, let's assume that it's only nearest neighbor and the j, because j, once again, jij very rapidly decays. So in practice, you can keep only the nearest neighbor. And then let's assume we have some constant j. What is this? Nothing but what you are familiar with as a Heisenberg model, right? For ferromagnetism. So you see, the coefficient here is originating from Coulomb interaction. It's not magnetic in nature. That's why it's also big, right? Because it's a large energy scale. And it can give you, critical temperatures for the ferromagnetism of hundreds or thousands of degrees even. But why is it there? And why is there a negative sign here, which favors the ferromagnetism? Because of the Pauli principle. Okay? So the same kind of exchange term for bosons will do exactly the opposite. Will enhance the repulsion, if you have repulsion, or vice versa. Okay? But the exchange terms can change the sign of interaction effectively. And that's a very interesting consequence. Okay? So, in a sense, this is the first already quantum effect that you see in a system with strong interactions. And both of these terms have matrix elements that decay with the distance, so they depend on two indices, but one can typically keep only the nearest neighbor. Now I'm coming to the third term, And I keep saying that one decays from the with the distance between I and j, but there is also a purely local interaction, right? There is an interaction term that is on one side. In fact, this could be the simplest one, if you like. Okay? The case where I equals I prime, I equals, okay, that's the third kind of interaction that we want to keep. Okay, so let me write it here. And in terms of its size, if you like, it's actually the biggest, right? Because there is, it's really on site. So let me call it, this is number 3, on site, or, because to keep the tradition that every interaction term is called after a person, this is called after Hubbard. So what is it? It's the case where I have only one index. All the indices are the same. And therefore, I have only one parameter, right? Because remember, this is all assuming that there is a periodic crystal, and therefore, because of the periodicity, the interaction as well as anything else does not depend on I explicitly. It's independent of I. It only depends on differences, okay, or distances between sites. So since this is completely local, you can just give it one letter, U, okay? It's constant. Now let us see what does it give. So let's call it H Hubbard. And so it's given by 1/2 U times, now I'm summing only over 1 I, and I have sigma and sigma prime. And now let me write down the expressions. I do it a little slowly. So all the site indices are the same. But what is different is the spin. Okay? Now, I'm writing it like this, just copy-paste the general definition. However, in this case, what happens if sigma equals to sigma prime? I get 0, right? Because they are fermions. So in fact, although it looks like I have 4 terms here for each I, actually I have only 2. Only sigma equals minus sigma prime. And because I have 2 such terms, either up, down, down, up, I can eliminate the factor of 2 here, of half, sorry, and I have just U times sum over I, and then if I'm plugging here some, let's say sigma prime equals up and sigma equals down, I have, or vice versa, it doesn't matter. This is just the number operator of electrons at site I with spin up, and multiplied by the same thing with spin down. Okay. Yes.
on the same site, can there be two electrons, one with spin up?
Yes, that's the only case where
Yes,
this
so-
contributes.
Yes, so, but
Okay.
in the previous case,
The previous case,
on the
we
exchange,
had all the possibilities. We had all the possibilities, but we had one term that looks like another term that is in fact identical
yes,
in the hard tree, but with a minus sign.
yes, that's something.
It doesn't necessarily cancel it completely because the matrix elements are different. But we had all the possibilities.
Yes, but about that, if you got spin up on site I and the particles on J, which is interacting with all the spin, so it
No,
can
but-
be exchanged.
Yeah, but you can still have an exchange. You can still have. That's the thing. If you take two electrons with the same spin, you can still exchange them. And there is such a term. There is such an operator, and indeed it reduces the repulsion.
But
Right.
you can exchange only if there is no another electron with the same spin on one of the sides.
No, that's right. But that's what this term describes. Okay.
How
You are simultaneously exchanging them. if you like. That's an allowed. There's no problem with that, right? Because the I and
No,
J
but
are
it's-
different.
But it is no. It does not include anything about other electrons on the same side. So how can this?
No,
This actually allows it.
I didn't tell you. I didn't tell you in advance. This is first of all, it's an operator.
Yeah.
If you want to see if maybe it has for some states or some electron occupation, it has zero expectation value, right? But you are right that of course. Let me put it in the following way. First of all, on each side, if you just look at what states are allowed for fermions, you cannot have a state where you have two electrons with the same spin on the same side. Okay? You can have, you can have this, let's say this is I. I mean, if you have, let's say, a full occupancy, okay? You have this J and you have this and this, okay? Now you can have all the possible hopping processes.
But not all the exchanges.
No, what's the problem?
You can't exchange one up and with one down.
No, I mean, if I do it simultaneously, there's no problem.
But after the exchange, you get two with the same spin
No.
on the same side.
No, I can tell. No, you're right that. Okay, so. I mean, I'm not sure what You can have a process where you exchange these two. Okay, you do it simultaneously, so the other spin is not. You're not touching it. There's
Yes,
no
but
problem.
The result of the exchange.
The result of the exchange
Can
is that
give
the
you
state
something
you're going to the same state. In fact, only you switch them.
But
That's
both
allowed.
the spins
That's
are-
allowed. What's the
That
problem?
if the spins are equal.
No, but the other electron already disappeared from them. It's like you take two particles, that you only allowed one per box, okay? You can do this. You can swap them. There's no problem.
But here you allow two electrons on the same place.
Yes,
the
but
same
but here it's a product of two densities.
Yeah, and going back to the exchange.
No, but there is no exchange here.
No, in the second lattice interaction with the Fox.
What is the problem here?
set.
Okay,
If-
there's no operator here that is identically zero, right?
No, but I think he means assuming I and J are both fully occupied, and sigma is different
Yes,
from sigma
that's what
prime.
I mean.
And sigma is different, then okay.
Then Pauli exclusion principle.
Okay.
Shouldn't allow
Now,
this
so now you're
exchange.
telling me that there are some states for which if I apply this interaction it will give zero.
Yes.
That's always true.
Yes.
That's true for any operator. Okay.
No, but I don't see why these operators should return zero in this case. Even for Pauli exclusion principle shouldn't allow this case. Because if you don't
I'm sorry, I don't.
No,
I
because
don't
you are applying
understand.
twice a day.
You are so that this operator just does a swap. It doesn't. It just if you had a legitimate state, it brings you to a legitimate state. It doesn't create in any stage. It doesn't create two electrons in the same state. Okay, so maybe we can discuss it afterwards. But I don't see the. I'm sorry, I don't see what is your problem. Okay. But here there is a case. There is a case that is identically zero, and that's why it's just not there. Okay, and that's why you can write it like this. Okay. So this interaction contributes something to a state that is doubly occupied. In fact, what it does, if U is repulsive, it raises the energy for occupying the same site, and you are allowed to do it if you have two electrons with opposite spins. You are allowed to put them on the same site, but it costs you a lot of energy. Okay? Now, because of that, you can gain energy by hopping electrons away from this site. Now, as a result, now let me give you an interesting consequence of such an on-site interaction. Is the so-called Hubbard model. Which is sort of the simplest strongly interacting model you can write down, that is really non-trivial, and it can give you a lot of interesting physics depending on the ratios between its parameters. What is the Hubbard model? So you assume a Hamiltonian that has a single body part is just the tight binding. So it has minus T ij nearest neighbor and and sigma of aj dagger ai. Okay, that's a single body part. Notice that when I write it like this and I'm summing all the nearest neighbors, I don't need to add a Hermitian conjugate because J and I are just dummy indices. Okay, so this is a hopping term plus the Hubbard interaction. This is called the Hubbard model. And what kind of physics it describes? And by the way, it is believed to be a good approximation for some materials like the family of the so-called cooperates, which are the high-temperature superconductors. What is the physics? First of all, you have repulsive on-site interaction. In the model, you only account for the on-site. So electrons on different sides don't feel each other, so to speak. But the two parameters here are U and T, and if U is much larger than T, then it's really not favorable to have electrons living on the same site, right? To have double occupancy. Now imagine that you are filling the band to half filling. So on the average, you have 1 electron per site. Okay, that's called half filling. In that case, the hopping term allows you to jump from one side to another, and if you happen to have a state where it's doubly occupied, you can gain energy by a process where you take an electron from this side to the neighbor and back. You can show, and you will show it actually in one of the tutorials, that you can gain energy from this by doing just second order perturbation theory. Okay? As a result of such a hopping is possible only if the neighbor side, so let's say I have some side and J, and here I have an electron with spin up, and here I have also an electron with spin up. That's not good. Why? Because
you cannot jump.
then you cannot jump. Okay? But if I have the neighbor is opposite spin, I can actually gain energy by going back and forth. Okay? So therefore, one can prove that the favored ground state is going to be an anti-ferromagnet, where the neighboring sides favor opposite spins. Okay? Yeah.
But this cycle, I mean, I'm assuming the probability that it will happen, I mean, spontaneously is very, very low.
No, okay. What I'm describing here is a pictorial thing of what actually you have to do a calculation. Right? Eventually, you have to solve the problem by doing some calculation, and you can do it in some perturbation theory where this term is smaller than this, and you are going to do it just for a simple case of two sides. Then you can show that it favors. So there is, in fact, an effective exchange energy, but once again, it's all coming down to the Pauli principle, which prefers anti-ferromagnetism for the same repulsive interaction. Okay? So these examples only show you that there are various mechanisms by which you can get magnetism. Okay? From something that, if you boil down to the microscopic exact model, it is just a Coulomb interaction. Okay? Okay, so the details of what I said, you're going to see it in the tutorial, but I explained the physics. Okay? And actually, now, to be fancier, there is a belief which cannot be, it's really a very hard problem to solve it in general, but there is some belief that if you are going away from the half filling, you can get superconductivity from this. But okay, the jury is still out if this works. Okay? Okay, so these are just interaction terms, and I already gave you a hint that sometimes it's favorable to treat them in a limit where it's actually the single body part that is the perturbation and not the interaction. Okay? Okay. Okay, questions about this part?
If you would like to write an nearest neighbor interaction, it will be like Ni and J.
Yeah, so the nearest neighbor interaction will be either of the, so there are actually the direct term and there's an exchange, okay? And of course, both of them exist also for higher order neighbors, but it's negligible. So usually, you're going in really nearest neighbors for these two, and Hubbard-like for electrons with a spin. These are the terms that we don't, okay? And you can characterize them typically by only three parameters. Okay, so now I'm going back to the story of doing perturbation theory. So I gave you a lot of physics motivation. You see, we can get also interesting things. Now we want to be able to do calculations. And so we need to learn a bit of formalism in order to do it, and then apply it for several examples. Okay, so now this what I'm going to tell you now is not necessarily only for fermions, but we will see what it does for fermions. Okay, so I remind you what is the idea. The simplest thing we can do with interactions when we cannot solve is to treat it perturbatively and get corrections to the energy, to first order and perturbation theory, which are of this type. Okay, the expectation values of the interaction in the ground state of the non-interacting state, and the non-interacting state is typically some kind of a Fock state. Okay, and now I'm not restricting myself to fermions necessarily, so it's something of the form, some product over lambdas of a lambda dagger to the power n lambda acting on the vacuum. And technically, the calculation we want to be able to do is to calculate such expectation values. Okay. Now, we saw that for fermions, actually, it is useful to replace the vacuum by this ground state, if the ground state is a full Fermi C, and then define operators that are excitation with respect to that. So the general problem that we need to look at is how to calculate, vacuum expectation values of general operators in second quantization. Okay. Now, to do that in general, let us first consider an operator, okay, that is a product of some string of many operators, okay? And it can be 2 body, 17 body, doesn't matter, okay? Some operator. And the A's and B's are A's and A daggers, okay? And I'm assuming this. I have some vacuum. For the time being, I call it 0. Okay, so what it is, now you may want it to be the full Fermi C or something else. Let's just call it 0. There are some annihilation operators. And all the A's and B's are taken from this sets, okay, where the lambdas run over all the possible quantum numbers, okay? So this is a general operator, and I want first of all to define a normal order I already mentioned it before when we just started discussing two-body interactions, but now I want to make a formal definition, okay? And I introduce a notation for normal ordering, which is to put two columns on the two sides of the operator. And the definition is the following. I take this string and I reshuffle the A's and A daggers so that all the daggers are on the left and all the A's are on the right. Okay? So after the reshuffling, what I'll get is, first of all, a phase factor zeta to the power p times a product of some A daggers times product of some A's. Okay? And here lambda and lambda prime are not necessarily all the possible quantum numbers. So when I'll give you some examples, but A, B, C, D are, some of them are A dagger, some of them are A. You can have special cases where all of them are creation and all of them are annihilation, doesn't matter. But either way, you can always take an operator and bring it into a normal ordered state by doing this reshuffling. Okay? Okay? And this is called the normal order. Now, why do we like operators at normal order? Because, why they're convenient? Because by definition, they have a zero vacuum expectation value. Okay, all the annihilation operators are on the left, and therefore it annihilates the vacuum. Okay, so this is true by definition. Okay. By the way, you can ask, okay, what if my operator is only creation? Then it is also zero because it's acting on the left, right? So it's always zero. Okay, very good. Now let us define, let us look at a special case of such an operator where you only have a product of two. So let's look at an operator that is just A times B, and I want to see what is its normal order. And again, A and B can be two creation, two annihilation, one creation, one annihilation. There are four types, if you like. But now what is the normal order of this? So, okay, AB, normal order. There are only two possibilities because there are only two, right? So normal ordering is reshuffled so that the annihilation is on the right. Now, it's possible that as it is, it's already normal order. Okay, so then this is equal to AB times, if already normal order. But if it's not, what will be the normal order? It will be zeta B times A. Okay, why just zeta? Zeta is, I remind you, is the +1 for bosons and minus for fermions. Okay, that's always our convention. So because there are only two, there's only one transposition. It gives you a plus or minus sign. Okay, if not, no. Okay, only two possibilities. Okay, now let's go further with this. I now want to define the following object. I take the A and B and I put such a sign on them. And here is the definition. It's AB minus its normal order. Okay? Now what is it? Again, there are two possibilities. If AB is already normal order, you get 0. What if you don't have a normal order? If it's not a normal order, then it's the other option. Then it's AB minus zeta BA. But what is this? And remember, A and B are, each of them is either A dagger or A. So this is nothing but what we define as commutator for bosons or anti-commutator for fermions. Okay, that's the. So, in other words, that's we write it like it splits to two cases. It's a commutator for bosons. It's an anti-commutator for fermions. Okay? Now what can I say on all these possibilities? In all these possibilities, this object, which we call a contractor, okay, so it's like you take two operators and you stitch them together. The result of this operation, all the three possibilities give you a number. Okay, no longer an operator. Okay. So, and this number is either 0 or a commutator or anti-commutator. Okay. So, in fact, if I'm considering some set of creation and annihilation, there are 4 combinations you can think of that I can call AB. There is A dagger, A, dagger A, and A dagger, right? So we can write down the contractors for all of them. Okay? And let's see what we get. So A lambda, let's first look at the contractor of some A lambda and A u. What is this contractor?
0.
This is 0. Why is it 0? Because it's already normal order. Okay, similarly, this contractor is also always, it's also 0. Okay, what about this contractor? also 0, right? Right? So what is not 0? Something else.
Integer A with the same.
So this is not 0 because what is it then? It's the commutator, either the commutator or
But
anti-commutator.
it's 0 here. Because
No,
they have
why?
different index.
No, they're not different. I didn't tell you that lambda
Ah.
and you are different, but you are right. If they're different, it's 0.
Delta.
But if it's not, it's either the commutator or the anti-commutator. In both cases, we know what it is. It's delta lambda. So you see, it's a very, very convenient object, this contractor, because it also doesn't distinguish between fermions and bosons. Okay? Now, why is it useful? Because now, if I now want to know what is the, I have some operator of this type, and I want to know what is its expectation value, its vacuum expectation value. Okay, so let's see what it is. Okay. So this is, we want to check what is this, okay? And I'm now going to easily prove to you that it's going to be nothing but the contractor, whatever it is. Why? Because let's look at this. This is the definition of a contractor. It's the operator minus its normal order. So if I'm just switching the order, I can write it like this. AB, the operator, A times B, is the normal ordered version plus a contractor, right? Therefore, its vacuum expectation value is the expectation value of the sum of these two terms, but the first term gives you 0, right? The vacuum expectation value of normal order of any operator is 0. Therefore, the only contribution is the contractor, okay? And since the contractor is a number, the number may be 0 or 1, right? But whatever it is, because it's a number, its expectation value is itself. It's just a C number. So we get actually a very useful expression. The vacuum expectation value, the vacuum expectation value of a pair of operators, A dagger, is the contractor. Okay? Okay, very nice, but this is by itself not that useful. It's kind of trivial because this kind of operator is a single body, right? It's something that doesn't involve interaction. And we would like to calculate expectation value of something that has at least 4 operators, right? Okay. But I'm claiming there is a theorem, and it's called Wick's theorem, which can relate such expectation values to summation over pairs. Okay, for a pair, we know the answer immediately. But when we have more than a pair, we have a string of many, many operators, we can always split it into products of pairs. Okay? And then we can, each of them we know the answer for. And
This is came from entanglement monogamy.
what?
This is related to entanglement monogamy.
I don't know what it is. Sorry. Okay. Okay. So now let's assume that I have some more complicated operator, which is a string of W, Y, Z, a lot of operators. And now I want to define a constructor of, among the many operators, I'm contracting two of them, let's say B and W, okay? Now, what is it? Actually, let me be a little more careful. I have some. Let me look at this. So this is my operator, and now I want to I'm looking at a normal ordering of this operator, but the B and the W I'm contracting. Okay? So what does it mean? I have to define what this operation means. So what the operation means is I first of all reshuffle W to be near B, right? Because then the contraction is very clear. It's just what I defined before for two operators. But when I reshuffle it, I pick some phase, okay? And the phase is, okay, there is some Z to the P, where P is the permutation, the parity of the permutation. After I did it, I got BW contractor, which is a number. And if it's a number, I can take it outside of the normal ordering. It's just a number prefactor. So let me call it BW contractor. And all the others, I'm leaving. Okay, that's what it means to contract two out of many. Okay. Now I can repeat this many times. I can now contract B and W and A and Z, and okay. Each time, what am I doing? I'm plucking two and taking them out. If I do it for all of them, and for that to give me something non-vanishing, what do I need? I need to have an even number of operators, right? Then, if I contract all of them, I get just a number. Okay. Now, okay, under this definition, one can prove, and that's the proof of it is some kind of an induction proof. I think Sar will do it in the tutorial if he has time. If not, we'll post, it's very technical, so we can post the notes. But you can believe that it's true and it can be proven mathematically, and we are going to use it. It's very useful, and that's the Weeks theorem. Here's what it says, that And I remind you that for each, the pair of each operators, its vacuum expectation value is the contractor. Okay? So if you have, let's say, 6 operators and you contract all of them by pairing, like the product of 3 pairs, and you just get a number. And therefore, the vacuum expectation value of that is just a number. Okay? So Wick's theorem tells you the following, that the vacuum expectation value of an arbitrary string of operators, A's and A daggers, of course, is given by sum over pairings. Okay, so you have to divide the string to pairs, and there are various ways to do it, right? If you have 4 or 6, you have many possibilities, okay? But you just divide them to pairs, and each division contributes a product over alpha of alpha b contractor of AB, and there is actually a very important number up here, which is zeta times the parity of the reshuffling operators that you need to make to get them into pairs. Okay? And it looks a bit abstract, but I'll give you a very simple example of the 4 operators. That's actually the case we're interested, because we're interested in 2-body interactions. And for that, it's easy to see that you're going to get only 3 possibilities. Okay, I'll show you in a minute. Okay, but this is what the Wick's theorem tells you in general. Okay, so in fact, it gives you a formula, a prescription for a vacuum expectation value of any string of operators, and what you get is this. You have to first look for all the possible pairings, and by pairing, what I mean is that you take the string and you put contractors on each pair. Okay? Yeah?
What if there is an odd number of
then what you get is 0. Okay, so first of all, when you have a string of an odd number of operators in the string, you always get a 0. Why?
Because each pair has
Because you see, just look at this, right? So I can pair 2 and pair another 2. Okay, but in the end, if I started from an odd number of operators, I'm left with a normal order of something that doesn't have a pair, and that one has 0 expectation value. Okay? So in other words, I mean, it's really clear that we know that, so that A and A dagger, right? So what you get after the pairing is that you get a number times A or A dagger. And A dagger of any state is always 0, right? Okay, so very good. So that's why, so a process. So you can have in interaction terms that it's actually good that you're bringing it. You can have interaction terms that involve three operators. That's a simple example for an odd number. For example, you can have a process where you scatter an electron from state k to k prime and you emit a photon. Okay? That process by itself doesn't have an expectation value. What can have an expectation value is the square, or if you do, you can have a matrix element, so it can bring you, so what it does, it can bring you a finite matrix element between a state that has a photon and state without a photon. And then in second order perturbation theory, you can get something, okay? But by itself, it doesn't have an expectation value. It has only off-diagonal matrix elements, okay? In some Fock space. All right, so so let's take the example of a four operator thing. Like this.
Just a second. We're talking about like summing all the pairings.
Yeah.
Right? And you said summing all the possible pairings.
All the possible pairings.
Okay, like also like overlapping.
Yeah. So you have you have only a finite number of possibilities.
Yeah, right, but not as you did before, right? That you chose two and took them aside, and you.
No, yeah.
Yeah,
Eventually, when in each pairing, I do a simultaneous. I pair all of them. Okay.
Okay. Yeah,
Okay, that's what I mean by pairing.
Okay.
Okay, and after you do it for each pairing, you just get a product of contractors times a phase factor. Okay, or more correctly, a sign. Okay, so let's see what we get. For an interaction term. So suppose we have, so we have, let's write down a general interaction term. So it's a sum of lambda prime, mu prime, v, lambda prime, mu prime, a lambda dagger, a lambda prime dagger, a mu prime, a. Okay, that's the general interaction term. And now I want to compute a particular expectation value of, actually, you know what, this is a bit too specific. This is even, okay, so I'm going to get to that, but let's first, just to clarify the formula, let's consider an operator that is just a product of four things, and at the moment I don't care what they are, okay? And so what the Weeks theorem tells you is the following. I'll write it first in colors. We use three colors because there are actually three terms. Blue. Yeah. Okay. So I have let me write it explicitly. A, B, C, D, E. Now I'm writing each pairing in a different color. What are my options? I can pair this with this. I can use color for reasons that I want everything to be consistent later. Okay, so this is one possible pairing, right? A, B, and C, D. Another possibility is to take A and C and B and D. Okay? A third possibility is A with D and B with C. And you agree that that's all, right? So there are actually only 3 terms, and they're going to be, and write down the result. And it's very important to keep track of the zeta here. So it's going to give me, the first term will be this contractor times this contractor.
0.
And this appears with a plus sign, right? Because we don't have to shuffle anything. Now the purple one will also have, it's AD and BC. This also comes with a plus sign, right? Because to shuffle D to A, I need to do 2 exchanges. So it's an even number. So there is a plus sign here always. But now there is a zeta, and that's the blue option is to contract A with C and B with D. And if they are fermions, this contribution will have a negative sign. Okay? And it will be, not surprisingly, related to what before called an exchange. Okay? So this is the term that knows about the statistics. That's like the quantum part. Okay, now let's apply it for general interaction. But notice that for an interaction, and now I'm back to the fermions, okay? So if the zero was truly the vacuum, then we have all these contractors for the vacuum. But notice that if I have interacting fermions, we already noticed that what plays the role of a vacuum is rather not the vacuum, it's the full Fermi sphere. Why? Because again, our purpose is to compute expectation value of the interaction, not in the ground state. That's trivial, because if it's written like this, you already know that it's 0. We want to calculate it in the ground state of the non-interacting system, right? And that's a Fock state. That's in the case of fermions, it's a full Fermi C, right? So this is what we want to. This is our goal. We want to compute this expectation value. This is what we are after. Okay? And for that purpose, we can use the expression for the interaction, but we have to keep in mind that it is useful to convert the A's and A daggers to the quasi-particle operator C that we defined before. Okay? And this, in terms of the C's, you are going to get these contractors. Okay? Because the Fermi C for the C and C dagger, it's a vacuum. Okay? All right, so let me just quickly say what we have, and then we'll continue with this later. So we take one particular term out of this with dummy indices, and let me write it down. A dagger, A lambda prime, dagger, A mu prime, A mu. And I want to compute the expectation value in this in terms of okay. So what does the weak theorem tell me? That I have three terms, and these three terms, let's be a little careful. I'm writing them as contractors of, so let me just follow the general definition. I can even use the same colors, okay? So the first term will be A dagger lambda A lambda prime dagger contracted, and A mu prime contracted. Now what is this? And when I'm writing this, what I actually mean is convert this to the C and C dagger, and then define the contractor. According to the vacuum, okay? Maybe we'll do it more carefully next week, but already here you already know what this term does. What is this? This is always zero, right? I mean, because even if we convert this to the quasi-particles C and C dagger, each of them is going to be either C or C dagger, depending on whether lambda is inside or outside of the Fermi sphere. But the contractor, the only case it can give you something non-zero is if lambda equals mu. And that will never give you, it will never happen, because if lambda equals mu, then if lambda equals lambda prime, then both of them are either creation or annihilation. So it will always give you zero. Okay? Now, having said that, there are cases where such operators can give you, such contractors can give you something non-zero, but that's when the vacuum is not a Fock state, but something else. Okay, and that we'll see later. We'll see an example for that. Okay, but if the ground state is just a Fock state with well-defined number of particles, this is always zero. Okay, so there are actually only two non-zero terms, and now I'm really focusing on fermions. So the first term is, which I denoted by purple, is contraction of A and D and B and C. What is it in our case? It's A lambda dagger A mu and A lambda prime dagger A mu prime. Okay? And now these things can be non-vanishing provided some condition on the mu's, and we'll do it next time, but it gives something. Okay? It gives something that depends on the occupation of these quantum numbers inside the Fermi suit. Okay? Yeah, something bothers?
No, I just thought that maybe the other one can cancel it, but no, I'm just doing it.
Now the other one, okay, and the other one, of course, if the indices are, for some indices, things can cancel, but the other term, the last term, for fermions, will appear with a minus sign. And that's the contraction of A lambda dagger with A mu prime and the contraction of lambda A dagger lambda prime with A mu. Okay? And whatever it is, in the cases where these are non-zero, this will give you a delta lambda mu, delta mu prime, mu lambda prime, and this will give you delta of lambda mu prime and delta of lambda prime mu. And therefore, they will not generally cancel each other. They will give you a difference between two different matrix elements, and they are going to be nothing but the direct and the exchange terms. Okay? So this will continue with this next week. Okay? But basically, you see that it's not so complicated. Eventually, this calculation is one line. Okay? All right? Okay. So, good weekend. כן, כן.
אז אמרנו שאנחנו נתחיל עם, יש לנו אלקטרון ב-I, אלקטרון ב-J, ואנחנו מחליפים ביניהם.
כן.
אבל בביטוי שקיבלנו לא היה שום משמעות אם יש עוד אלקטרון באטום באטום I ו-J. וזה יכול ליצור בעיה עם הפאוליק.